Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullah. Peace and blessings upon you all. Dear students, today we're gonna deal with the binary search tree. Okay, BST. It is a binary tree with some additional properties. What is that property? And that property is the symmetric order. Okay. What does that symmetric order means? That every node has a key, and we have a node. Okay, for example, and every node has a key with a left child and a right child pointers with it, and this key, the data we talk about, is, for example, here we have the n, okay, which is stored in a node, particular node. The property is that this n should be greater than whatever the left on the left side we have in a left subtree. Okay, that means it should be greater than all the, or larger than all the keys in the left subtree, and it should be uh, less than whatever is the n is. It should be less than all the keys, less than or equal to all the keys on a right subtree. That means if we have some data, say for example we have 10 here, for example, and everything lesser than 10 gonna be on this side, left subtree, and everything thing greater than 10 gotta be on this side. So whatever is here is gonna be greater than or equal to n, and whatever is here should be less than n. Okay, so if we have, for example, this thing, if we have these keys, so how we present, so first we have 13, so we put up a 13 here, for example. Then we have 7. Okay, so if I say 7 here, so what is 7? Lesser than 13, so it should go on the left side. Then 23, so we start from 13, 23 is greater than, so we should put up on this side. Then 4, 13 lesser, 7 lesser, so go here. 8, 13 lesser, 7 greater, so go on the right. 17 is greater than 13, so go this side. Lesser than 27, so put up here on the left of 27. 3, lesser, 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 go 3 here. 5 is gonna be on a value of greater than 4, so 5 is here. 1 is all gonna be lesser, 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 so 1 is gonna be on this side also. Okay, so this is 1. 9 is gonna be, you go here. 7 greater than 7, greater than 8, so 9 is gonna be here. Say for example we have here 14. Well, 14 go. 13 greater than 13, lesser than 27, and lesser than 17, so on the left of this is it. If we have, for example, 30 greater than 13, greater than 27, 30 gonna be here, and so on. Okay, now this binary search tree, what it does is you know, optimizes the searching. For example, if you want to search, say this key 9, say you want to search the 9. Okay, so we are gonna search the 9. So when we go here on 13, okay, we know the 9 is surely on the left side, so all of this right side you can skip it, whatever is there, whatever all nodes. So problem is solved in a half, like we have binary. That's so in a binary search we have seen it is kind of same thing. So it reduces at this node, that whole it compares with this, I know it's on left side. So when I go here, I know it's going to be on the right side. Now this much is reduced again. When I go to the 8, I know it's going to be on the right side, and I got it. So only 3 iterations I will take to find the 9. Okay, in a binary tree you could have seen, yeah, you got to see, you know, every node and chuck in where it is. But here we know that we can skip at every step, you know, kind of a half of the tree. Firstly the half of tree skip it. Okay, then on this side the left of whole of this is skipped, and so on. Okay, and this will happen with the searching of any node. Now if you have to find the, for example, the minimum or the maximum, these are some properties we're gonna see. And the operations actually we gotta have here is the searching, find minimum, find maximum, insert, delete, and sometimes successor and predecessor. These are also need to be found. Okay, now when we work with them, we find that the complexity of each of these is big O of h, where h is the height of the tree. So at an average, it will take whatever the height is. Okay, so if the height is, say for example 3, it will take in a worst case it will take 3 iterations to get to that, whatever the height is. Okay, say for example we have some 100 nodes or 200 nodes or 300 nodes. If we don't arrange it in this order, okay, then we have maybe in the worst case we can, if we have 300 nodes, it may take 300 iterations, but here it will take just 3 or 4 iterations. It depends upon the height of the tree. Okay, now in this the insert and delete are a bit more tougher, but the finding, the searching is so fast. That's why if we have more, like we actually are having searching operations more, so this will help us. Okay, it's a more efficient than the linear search, so efficient. Okay, but not that efficient what we do in the hashing, which we see later on. Now to find the minimum and the maximum, if we look at this tree, which is the minimum, it is gonna be the leftmost node plus 1 here. Okay, this is the one. It is the leftmost node that is gonna be the minimum, and it is the rightmost node which is gonna be the maximum. So this is the maximum and this is the minimum. Okay, so if we see the minimum element is the leftmost node and the maximum element is the rightmost node. Okay, now how to find the minimum? So you will run a while loop while x arrow left is not equal to null. Okay, I will show you its little representation also. Now if you see this, we have a node and it has a left pointer and a right pointer. Okay, left pointer points this, right pointer points this, and so on. And if we have on the left, say for example another guy like 3, so this will be like this. Okay, if we take this implementation, we have a 3 here, and then there will be null here. Say for example on this side there will be 1 here. Okay, then it's a null here, right? This is a 1, for example. This is 1 in it. Now here is null, here is null, so that means this is the last one. So this is the minimum. Okay, so we're gonna go from this side. So here it will not be null now, it will be the address of this guy. If its address is, say for example, let me call it in a simple way, like its address is 100, so here will be 100. Okay, if its address is 50, say for example there will be 50. These are addresses, for example, and in this will be the address of this guy. So this is filled, this is filled, this is filled, and this one only is a null because there is nothing on the left. So we got to go on the left side until we find a null. So when we find a null, that guy is the minimum. Okay, so that's what we do. While x arrow left, so x arrow left is this, whatever the x is the root. In the beginning we send the root to it, so that means this is the x. Okay, the root. And is x arrow left, because x arrow left is this null? No, it's not. Go. X is equal to x arrow left. You put into the x arrow left, whatever the address here is, that is 100 for 50. Put that in the x, that means now x will point to this. Okay, is x arrow left null? No. So then put whatever is x arrow left, that is 100, to the x, so that means x is pointing to the 100, that is this node. Okay, so x is pointing to the 100 node now. Is x arrow left null? No. So go forward same way and x now point to this. Is x arrow left null? Yes, it is. So we gonna return this x. Okay, so that's x is this guy. Okay, and we know this is the minimum. And same way we're gonna go on the right side to find the max, because this will have a null, because this has the address of this guy, this has the address of this guy, and so on. So we gonna go for the max. First we send the root. Okay, then x arrow right, I will see is that null. If that's not null, go forward. How? X is equal to x arrow right, and go on. And when you go here, x arrow right, you go here, and when you say x arrow right, that's null. So you're gonna stop, you're gonna return this, so x will return the 99. Actually address of this, then we can print that is the maximum of that tree. Okay, now for searching we're gonna do the same thing, but should we go to the left or should we go to the right? It depends upon what we are searching. So key, the key we search, is that less than this 9 or greater than 9. Say if it's less than 9, then I will make x is equal to x arrow left, and if it is if it's less than 9, if it's greater than 9, I will say x is equal to x arrow right, so that I will move on the right side. Okay, so the combination of these two is actually going to be the searching. So this is my search function. Okay, and I'm searching for the key k, the value k, and I will firstly this search will start from the node, so I will send it node, and it also returns that particular node. It returns the node that is of type node, that structure, that pointer, which will point to the particular, when we have found it, will actually return that. And I'm saying while x not equal to null and k not equal to x arrow key, if I have not found it and it's not null. So if it is null, for example, I was trying to find it and I came up null, that means it's not there. Okay, if it is not null and it's not that what I'm finding, so I should go forward. So for example, firstly I go to the, I have a root, in this case I'm setting it root is, I'm talking of this guy now. Is this the null? No, it is not. And is it what I'm finding? For example, I'm finding something like 97. Is this what I'm finding? No. So I should, that means this is both true, so I should go down. Now since we're talking about 90 something, like a second, I will say for example talking about 97, which happens to be greater than 9. Okay, so I will say here, if that key that's 97, is that 97 greater, less than x arrow key, is a less than or greater than. So because x is this time pointing to the, is this guy, is it x arrow key, whatever it is, that's 9, is that 94 less than this or greater than this? So depending on that, because definitely it's gonna be key is not less than this, so I should not go to the left, rather I should go to the right. Or if I would have been searching for 5, then I should have gone on the left side, x arrow left. So I should make x is equal to x arrow left. That means it will point to this guy. Now I am talking 97, so it will go here, right? X is x arrow left, so x will point to this guy on the right side. Okay, it's not gonna stop, because I'm again saying, is x not equal to null? Yes, this is not null. And second thing I'm saying is key, whatever finding out k, is that not equal to x arrow key k, is it, that's what I'm saying. I was finding 97, is it 97? It's not. So both are true, so we should go forward. So should we go to the left or should we go to the right of this? Depends upon the what I'm finding, that's k, that's 97, is it lesser than this or greater than this? It's greater than this, so x is equal to x arrow right. So whatever is on the right side, that will point to the x will get that, so that means x will point to this guy. Now again I'm saying, is this null? It's not null. Or is it not equal to what I'm finding? But it is equal, so it's false. So this guy is false here, so that means I have done. So I will return that. So I will return this guy. So I will return this guy, so that means I have found. Okay, this is how we work. And where we call the search, there we check that if there because we have checked for the null also, because maybe it's not there, so we will end up going somewhere which is null. Say for example I was finding 100, so it's not equal to, it will go forward, so x will point to this, and then it will go, because 100 is greater than this, so x is equal to x arrow right, that is in null, so x will have a null. So that this thing I will check where I call the search. If that when I call the search and it return me the null, it will return that x, basically it will return that x, and if that is null, that means the element I was finding it was not there. Other else I will print x arrow key, because x will be pointing to the exact guy which I'm finding, so x arrow key will tell me yes, that element is there and I have found it. Okay, coming back, actually I left this recording in the morning. Now this is 11:13 p.m. now. I don't know why it was. Perhaps I was on insert operation, so I put up the insert operation here. So I don't know why it was. Let us do the insert operation. In fact, mic is also down. I'll pull it up. Oh, I forgot to put up the mic. Hopefully there is voice. Now let's discuss the insert operation. Okay, so for example, you got here 20, say on this side 17, on this side 25, then I may have 15 on this side, and I have, say for example, 18 on this side. Then on this side maybe I have 22, and maybe I have this side something like 30. Now this was, say for example, this was our structure of a tree, and I want to add, say 19. Okay, now when you want to add 19, you have to first see whether the tree is empty or not. If the first thing is maybe the tree is empty, then this is going to be the first node, and then the root pointer will actually point to this. Okay, but if this is not the tree is not empty, so I gotta see where I should place it. Okay, if I do it here at 20, I will compare it with the 20, and it's lesser, so I should go on the left. So I should make my pointer point to the, because this 20 will have because every root node will have a data part and a left pointer and a right pointer, right? So I should make my pointer, whatever the pointer is at that moment, say it's a P or P, whatever it is. So P equals to P arrow left. In the beginning, P will be pointing to this guy, and then I have to make it P equals P arrow left, and here. Then I'm gonna compare again 19 with the 17. Is it lesser or greater than? Because there is 17. So it is in fact greater than. So I should not go to the left. Now right now here I should go to the right. Now because by making here P equals P arrow left, P is here now. Now here I have to do that P equals to P arrow right, whatever is in the right pointer, that's the address of this guy. So P will point to this guy. Okay, again at this moment I have to again compare 19 with the 18. Now it's again greater than the 18, so I should make P equals P arrow right, because in this case P arrow right is null. Okay, so this is the point where I should stop. So where I should stop when P gets inside the null. Okay, so here I should drop this new node. Okay, in which I will have a 19. Okay, you getting me? So simple as it is. So starting from the beginning, I'm gonna say left or right, and until I reach the point where that pointer P equals to null, and I drop into that 19 or whatever the node that is. Okay, all right, now let's see the piece of program. This is simple. Now this is the C implementation. You can do any kind of implementation you like. I'm lazy to write it myself, so I take it from here. This is the link, Geeks for Geeks. They have put up this good program, and I found it, just read it, and I found it's correct. Okay, you can do any kind of implementation, that's not a problem. You have to understand the concept. That's my job. Okay, I should tell you that maximum times I take up things from the internet and paste it here, so that I don't have to write. I have to only explain. Okay, I don't want to make my own PowerPoint files or whatever. I just all the time take it from the internet and just start explaining. Okay, so this is a program. We know all these things. This is our structure, which will actually create a node like this, which will have a data part. There's a key. He calls it a key, so this is the key, and it will have a left pointer and a right pointer. Right, this is the node. Okay, this is the structure. We got to, when we create a memory, we've got to create a memory for this structure. And this is a utility function which actually does what? Which actually creates a node for us. Okay, so it is called new node, and it returns a pointer that's going to be the address of the node being created. So if its address is 100, it will return the 100. Okay, and what you're sending to it is an item, which is the key. That is what you want to add. Okay, then actually you create struct node of this type. You create a pointer, a strict temp, and then you call a malloc. We know all these things. You have to typecast here, and then size struct node, and all those things are we have explained it in more detail in other videos also. so this is not a big deal. And then you put up into the key, because the temp will hold the address. So what will happen here is it will create a node like this. Say for example, create a node like this, okay, and its address is in temp, okay. And then in the temp arrow key, that's this guy, you drop that item which you have sent. For example, you send 20 to the item. When you call the new node, then the 20 will be put in here, and in its left and its right pointer, there will be null, okay. Now then this is an inner traversal. We discussed this thing. I'm gonna skip it. Then here is where we're gonna insert, okay. When we want to insert, we call the insert function, okay. We'll call the insert function. This insert function returns me the node, struct node, okay. And it takes up the address of the a structure. uh, mm, I call it as a put that in the node, and the key value. So for example, you want to put some 20, or in my previous case I put up the 19 perhaps, into that, yeah, 19. That got on the right of this. Say I want to put 19 and I call the search, okay. So that 19 actually is copied into the key. Now if tree may be empty, so this is going to be my first node, okay. So that's why I say if node equals to null. Okay, the node is here, like I usually take up the root. That is the node. If that is null, that means it has nothing in it. That means there is no tree whatsoever. So this is gonna be the first node. So I will return the new node, okay, with the key. So I call the new node. So new node is my method or function which actually creates the node. I call the new node and send it the key into this item, and it will create me the node with 20 and null on the both sides, and that its address, the temp, will be returned. And when that is returned, that address of this node, that single node that is being created, is returned also, okay, here in a new node. That is what I return here. So new node will actually create me the new node with the key inserted inside as a first node, and that address is returned. So this function, whenever it's called, it will return that address, okay. Okay, now if that is not my node, I have already some tree there. We have some nodes there, so it's not an empty tree. Then it will skip this part, okay. It will skip this part and it will go here, and here we have to see if key is less than node arrow key, because in the beginning node is my pointer, like I say p in an example, or sometimes I say root, okay. Any pointer which points to the first node, okay. That's the node is the pointer which points to the first node, okay. So node, if key is less than, now I have this node here, for example, and node is having the address. So my key is 19. Depending upon whether I should go to the left or right, I have to compare the key, this 19, with the node arrow key, is it? So that's why I'm saying if key is less than node arrow key, if it is less than 19 is less than this, I should go to the left. If it's greater than, I should go to the right, is it? So I should go to the left, and in left I again call the insert function, and now I send it node arrow left as the node address. Like in the beginning I send it, when I call the if I call the insert function here with the first time, I will send it the node, that is the address of the first node, right? Now I am sending it the node arrow left address of this node, okay. I'm sending the address of this node now. So that will be copied, because it's a recursive calling to itself, and that address is now in this node. Now node is not pointing to this, node is pointing to this, okay, and so on. And I put the key, I have sent out also the key. So again the comparison will be done on this node. If this is not null, if this is null, this will happen, this thing will happen at the end. When the null enters, this thing will happen. But if this is not null, so again the comparison, depending upon that, should I go to the left or the right, I will send to this insert call node arrow right or node arrow left, and so on, and recursively does it. And when it is say for example I go this way, and now again comparison occurs and I have to go this way. Now there is null, Okay, so the node arrow right, for example, I said node arrow right, like an upper example. Now that is the null. Okay, because in the because this node has nothing in this, so it was a null. Now null goes into the this node, and now this if block comes into play because node is null. Now it will create it will call the new node, which will create us the new node and send it a key, and its address will be returned. Okay, it will be returned where it was called, so it was called here. Okay, in so node arrow night. So whatever comes back, it comes back to the where it was called. It was called here, so it returns the address of this new node, and that goes into the node arrow right. It goes into the, say for example here, okay, so new node is created now. Whatever its address is, say for example 2200 or something, that will return. Okay, from here that return, and to return to where it was called. It was called last time, it was called here, so it will return to the node because node was previously here, right? It is node arrow right, that this guy here, it will be have the address returned. So that means that we have a proper link. Does it make sense? If you're not getting it, that means you have problems with the recursion. You should go to the other programs where I've seen the recursions, the link, single linked list, double linked list, then recursive examples and all. Then only then you can understand it. Okay, you can't come here without having a data structure, other knowledges, and start learning trees. Okay. Okay, so next is the deletion. Now deletion algorithm is a little more complicated, so that we're gonna do in a next video. Okay, until then, keep smiling and ma salama.